All right, let's talk about something you've definitely seen, but maybe never had a name for. We're going to dive into a concept from the history of image processing that, it turns out, is more important now than ever. We're talking about frequency analysis, and it's kind of like a secret weapon for anyone working with modern computer vision. You know exactly what I'm talking about, right? You resize a photo, or you zoom way in on a diagonal line, and it stops looking smooth and starts looking like a staircase. Well, those annoying jaggies, they aren't just some random computer error. Nope, they're actually a clue that points to something much, much deeper going on. And today, we're going to figure out what that is. So here's the game plan. First, we're going to put a proper name to that glitch. Then we're going to completely change how we think about images and start seeing them as signals. After that, we'll learn the language of signals, which is frequency. And finally, we'll connect all the dots and see why this old school idea is so incredibly important today. Sound good? Let's jump in. Okay, first things first. Those jagged edges, that staircase effect we were just talking about, it actually has a technical name, and knowing it is step one. It's called aliasing. You've probably seen it a million times, maybe you've even heard the term thrown around. It pops up when you're resizing, rotating, anytime you manipulate an image and things just get weird. But the really important thing isn't just the name, it's what aliasing represents. And this is where it starts to get really interesting. See, aliasing isn't just a problem with the pixels themselves, it's a frequency problem. It's a warning sign that we've misunderstood the actual information packed inside the image. So to really get it, we need to look at images in a whole new way. To get to the bottom of aliasing, we have to kind of borrow a page from the past. We have to learn to see images not just as a grid of dots, but as signals. Yeah, check this out. Today, most of us, especially if you're in computer science, you think of an image as a data structure, right? It's a big grid of numbers, something you load up in Python with NumPy. But if you rewind the clock 30 or 40 years, the folks who pioneered all this stuff were electrical engineers. And to them, an image was a signal, just like a sound wave from your speakers. And that classic way of thinking is what we're tapping into here. Even though our tools are completely different now, that fundamental idea that an image is a signal is still absolutely critical. It lets us see past the individual pixels and really understand the information they're carrying. So, if an image is a signal, how do we describe it? Well, that brings us to the language it speaks, the language of frequency. This is the key that unlocks everything else. To put it super simply, frequency analysis is just about looking at how fast the information in an image is changing. Do the colors and brightness change really quickly across a tiny space, or do they shift slowly and smoothly? That speed of change, that's what we call frequency. Let's break it down into two main types, which this table shows perfectly. You've got high frequency, that's where things change fast. Think about the sharp edge of a building or the detailed texture in a patch of grass. Then you have low frequency, that's the opposite, the slow, gradual changes, like a soft gradient in a clear blue sky. Every single image is just a big mix of both. And here's the connection we've been building up to. Aliasing is what happens when you try to resize an image, but your method just can't keep up with all those high-frequency details. There's this rule in signal processing that basically says you have to sample a signal at least twice as fast as its highest frequency to capture it right. When you don't, the system gets confused. It sees all that rapid high-frequency change and mistakenly turns it into new, fake, low-frequency patterns, and those are your jaggies. Which of course leads to the next question, right? What exactly is the wrong way to resize an image that causes all this trouble? Let's look at a super common but really flawed way to do it. It seems to make sense at first glance, doesn't it? If you want to make an image half as big, you just get rid of half the pixels. So you just go in and delete every other row, and then delete every other column. It's fast, it's simple, and it's a terrible idea. Because by just throwing pixels away, you're chucking out all that crucial high-frequency information without a second thought. You're not summarizing it, you're just deleting it. The right way to do it involves a crucial first step. You gently blur the image. It's called using a low-pass filter. This removes the high frequencies that the new, smaller grid of pixels can't possibly represent anyway. Then you downsample. By blurring first, you prevent the signal from being misinterpreted, and you get a result that's so much cleaner. All right, let's bring this all home. We've talked about jaggies and signals and frequencies, but why does this old engineering concept matter so much right now in the age of AI and deep learning? Because this isn't just some dusty old theory.
Understanding the world of frequency has a massive, real-world impact on anyone building systems that need to see and understand images.
I mean, when you get this, you can design way smarter filters and transformations that don't create ugly artifacts. You can avoid those distortions when you're scaling or compressing images. And this is a huge one. You can seriously improve the performance of your AI models. Things like aliasing and high-frequency noise can totally confuse convolutional neural networks, the brains behind most computer vision. Feeding them clean, properly handled images is step one to getting them to work right.
So, what's the big takeaway here? It's that even if you're living in a Python world, thinking of images as just data structures, grabbing a little bit of that classic signal processing mindset is a genuine superpower. It helps you see problems before they even happen, and it lets you build things that are just flat out better. And that kind of leaves us with one last thought. In the race to find the next big thing, it's really easy to forget the fundamentals. This is a perfect example of an idea from decades ago that's still completely essential. It really makes you wonder, what other old ideas are just sitting there, waiting for us to rediscover them to solve the problems of tomorrow? Something to think about. Thanks for watching.